Hello, my name is Derek Stuercke, and I'm a senior chemistry major here at Carroll College. Today, I'm going to be presenting to you one of my research projects that I performed in the integrated laboratory under the supervision of Dr. John Rowley. This project is entitled The Observation of Hammett Analysis via Cyclic Voltammetry for Solar Energy Storage. Now, the field of solar energy storage technologies has been an increasing field for years, and we feel that it is very substantial to contribute to this. Our contribution to this is as follows. We hypothesize that the quantification of the mechanistic and kinetic parameters for an oxidative homocoupling dimerization reaction results in the formation of a carbon-carbon bond at the para position of the thiophene ring is possible. The homocoupling reaction was electrochemically initiated by oxidizing the para-substituted phenylthiophenes via cyclic voltammetry. Our mechanism of interest is shown here. Now, this first molecule here, our starting material is going to be referred to as the monomer, and the final product here is going to be referred to as the dimer. We are expecting it to go through in reaction equilibrium, and this loss of the electron here in the first step is indicating the oxidative behaviors of this reaction. Now, as I've mentioned before, we are going to be doing this via cyclic voltammetry. Cyclic voltammetry is used for many applications in electrochemistry. More importantly, it is used to investigate oxidative and reductive mechanisms of chemical and molecular species. In order to do this, we also compared cyclic voltammetry to a biologic software simulation that allows us to compare the experimental data versus a simulation of that same data to give us more of an accurate reading on things. The reason why we want to perform this is so that we can perform Hammett analysis. By performing Hammett analysis, it becomes kind of the key point in improving the technology of solar energy storage. This analysis allows from identification of possible mechanisms for the oxidative dimerization homocoupling reaction, and we use these sigma para values that are shown here on this slide of the molecules that we wanted to be that we will be testing. My apologies. These sigma para values show us the free energy relationships in the sigma bonds that are being formed. And we anticipate a negative slope extracted from the math that we get on performing the Hammett analysis. However, I will not be discussing the Hammett analysis here, as our research showed that we were not able to test enough molecules of interest in order to discuss it. So I will mainly be discussing cyclic voltammetry and the oxidative behaviors of the reactions that we performed. As a sort of base molecule to help us discuss this, we look at ferrocene. Ferrocene is a very common reaction for us to observe because we are able to see both oxidative and reductive behaviors because it is a reversible reaction. Now, and you can see that by seeing in the minima of this graph shown here where my laser pointer is, that is the oxidative behavior of this reaction. And it cycles back, which is indicating the cyclic voltammetry here. It cycles back to show us the re-reduction of this same reaction, showing that it is a reversible reaction. Now, as you can see here, the blue is showing what we simulated on the biologic software, and in the orange is our concentrations. Now, the difference between these two, why we don't necessarily see them matching up, is due to the fact that the concentrations of the simulation versus the concentration of the experimental data was different, which is why we see that huge gap being shown here between this maxima and this maxima. Now, moving on to a molecule that we tested as well that is more of interest, not quite of interest because we want to test phenylthiophene compounds, but this is just a normal thiophene compound. This is 2-methylthiophene. We tested this at different scan rates because we hypothesized that by changing the scan rate of the cyclic voltammetry, we would hopefully be able to see that equilibria occur in the reaction that I discussed earlier, showing the reductive behaviors so that we can extract the kinetic parameters from the simulation. Now, as you can see, as us changing the reaction rates here, we are not seeing those reductive behaviors because this reaction going towards the dimerized product of this thiophene ring is an irreversible reaction. Using ferrocene is a very good indication of an irreversible reaction, but we wanted to see if we are able to replicate this on an irreversible reaction shown here. And unfortunately, according to our graph and our data here, we were not able to see that here with 2-methylthiophene. One of my colleagues, Chris Genin, did a UVVis spectroscopy of this nitrophenylthiophene compound shown here. And this is showing us the formation of the monomer reaction here, which is indicating that we are actually seeing what we are seeing. We are not seeing something that's going crazy. We are seeing what is supposed to be happening with an irreversible reaction. We are not seeing the reductive behaviors occurring, so we are not able to extract those kinetic parameters for further analysis. Now, to also contribute to this using cyclic voltammetry, we were able to do this sort of research with ethoxycarbonyl phenolthiophene shown here. And as you can see, in this area, this is our main point of concern. We were only able to test this at 1 scan rate, and at 1 scan rate, we are able to see just the oxidative behaviors. We are still not seeing that reductive behavior of the irreversible part of the reaction. So it is confirming that this is still an irreversible reaction. We are not seeing the reversible behaviors in order to extract those kinetic parameters. So thank you so much for listening. Our future directions for this project are going to be focused on analyzing cyclic voltammetry and using the biologic EC software fitting of phenylthiophene compounds, because the more we are able to do the fitting of more phenylthiophene compounds, that way we can perform the Hammett analysis that I discussed earlier. And also additional efforts should include investigation and better control of that EC biologic software. That biologic software was a little bit difficult to use and no one in the lab had used it before. So we are still learning how to use it efficiently for simulation and for extracting those mechanistic and kinetic parameters. Lastly, I would like to conclude by thanking Carroll College and the Department of Chemistry for providing me with the skills to achieve professional level research. I would especially like to thank Dr. John Rowley for the expert and continuous guidance throughout the duration of this module. And lastly, I would like to thank the E.L. Wiegand Foundation and the Mary Alice Fortin Foundation for providing us the laboratory that we were able to use, along with all the expert and professional level equipment that we were using. Thank you so much.